Anyway, it's fine. So this is review. So again, we want to mean this what f is from Q to R. Q is a subset of Rn, and then we consider f is proper LSC. Proper means epigraph is not empty. LSC means no semi-continuous. That means we allow jump. Okay, we allow jump. Okay. But anyway, not important. Of course, we consider f is convex, but here I didn't say that. Anyway, we want to minimize this, and then x has to be in Q. So solution feasible if it's this true. Infeasible, that means not true. Okay. And of course, Q constraint set we assume is convex. Okay. Then first we have inf. Okay. Min should be inf. This is just analysis thing, we really don't care, okay? But these are details. I'm not going to talk about too much on this. So what we do, we produce a sequence x1, x2, x3, x4 up to xk, and then so on. We want this such that this xk at k go to infinity, f of this value approach this value. What's this value? The smallest achievable value on all the cube. Okay, so this idea. And we call a solution approximately accurate by this. We don't need absolute value because this number is larger than f star. Because f star is the smallest one, so we can remove epsilon value. So basically means what? If my function value is smaller than the gap between my function value and the optimal value is epsilon, then correct. And you can say, I assume this is 0, then I don't care. Then they basically mean this smaller than epsilon. Something like that, right? So this is the idea. And what we want monotone. What's monotone? This is monotone. All the new is smaller than the old one. If this is not true, then this is not monotone. Easy. Then how do we proceed? We do this, right? Old point, step size, direction, new point. Okay. And if this we want monotone, this is gradient descent. So basically this is the idea. What is the algorithm? This is an abstract algorithm. Find a delta by what? By all the information you have right now under some theta. Theta is some parameter. If you have something, okay, step size, find all the step size using all the previous thing you have. Find the new point using all the information you have. And then lastly, find this theta if you have parameter. So basically these are all the things. Then the typical question is, what is this? What is this? What is this? What is this? These are basically design problem and algorithm problem. Okay, for gradient descent, we just what? Do gradient descent. But now here's the first thing. How do we choose this delta? The idea is this. You want delta inner product negative. Here's the proof. Why? Because if you do this, then the function value will go down after you do the gradient descent. So here's the idea. So f is convex. So I have this. Remember this? What is this? So f, this is x, I have a, I have b. Okay, gradient at b. This is function value. Gradient at b. F at this point larger than a straight line defined by the gradient of b. This f at this point will be this value. This thing is above this straight line. So convexity. Okay, now I have this. Put a is xk plus 1 and b is xk. So this is xk plus 1. xk plus 1 minus xk. And if I do this, then this bracket is just step size time direction. So step size time direction here become here. Other thing I copy. So now I have this expression. What is this expression? The t is number. Go out. So I have this expression. Now this thing larger than this thing plus this thing. So this thing subtract this thing larger than this thing. So I have this thing. By definition of descent, I want nu smaller than O. Nu smaller than O, that means this whole thing need to be negative. This thing need to be negative means by this arrow, this larger than this thing larger than this thing, so 0 larger than this thing. So I will have this. Because step size is always larger than 0. So this is the idea. If you have a delta that is negative to the gradient, you will guarantee function value go down. This descent direction. And gradient descent basically choose what? Gradient descent basically choose this as negative. So negative inner product with itself, so it's a negative norm something. Of course it's negative. Okay? So therefore, this idea. How do we pick? Well, gradient descent just pick this. Therefore, that's it. Now, next, gradient descent with a sufficiently small step size will converge. So what's the step size? This, you have seen this. So now we talk about it again. So this is what? Arrow smoothness. And then what? A is xk, and then b is xk plus 1, 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 xk plus 1. Then what? This is gradient descent. This subtraction become this part. So this is subtraction. So now this part here, this part here, this part here. Again, there's a t, there's a square. So it will take out. Okay, so I have a square here. There's a t, right? So the t is here. Okay, so now I have this part I go to this side, so that's why I go to this one. Okay, so now I have this thing. So now I have this part. These two things, both are what? Gradient, norm square. So I can further combine them. Negative t, this is L divided by 2 t square, so I can take a t out, so I have this thing. This is what? Nu minus O. What I want this thing negative. That means this thing smaller than this. So I want this thing negative. I want this thing negative. That means I want this thing negative. I want this thing negative. This is always larger than 0. So I don't care. I want this thing negative. This thing negative means without the negative sign means this bracket is positive. So I want this bracket to be positive. Then, okay, I rearrange this bracket. I will get something that looks like this and it will be a value t. That means I have this. What is this? Nu minus O. No, O minus nu. And this is what? Telescoping sequence. Okay, what I'm going to do? I'm going to do this standard trick. At k equals 0, I have this 0, 0, 1, 0, 0, 1. At k equals 1, 1, 1, 2, 1, 1, 2, and then 2, 2, 3, 4, 4, 5, and then what? And then I add them up. I add them up. This, all of them become what? Become this thing. This part, all of them become what? Here's a fun part. This is plus, this is minus. So if I add them up, they cancel each other. There's a plus f2 here. There's a minus f2. I cancel each other. So if I do this, what I have? All this thing gone. I only have this part and this part left. So that's what is f0? F0 is the starting point. It's just number. I don't care. Alright. So I have this whole thing thing smaller than something like this. Okay, in other words, I have this thing. If I have infinity, I take everything k go to infinity. This thing will be smaller than this whole thing k go to infinity. This is a number, I don't care. So a number. This is what? Something go to infinity. Assume this thing converge and is larger than negative infinity. Then flip the sign. You have positive infinity. Positive infinity plus anything is positive infinity. So I have something smaller, strictly smaller than positive infinity. Then you see the idea, right? Sum converge. That means each term becomes 0. Converge. This is converge. Okay, done. So this is the idea. So again, revision. I'm now talking about gradient descent is local quadratic. Basically, the idea is I'm talking about the idea this. Every time when you do gradient descent, you're actually having this picture. I'm talking about this. This slide is for this picture. Okay, let's start. You want to mean this gradient descent? Okay, now I use alpha step size. This has to be strict larger than 0. Okay, where does one come from? Now I said this thing is gradient descent is a solution of minimizing something. The answer is this thing is this. That means what? That means if you minimize this on x, you should get this. How? So I have this, right? This is what you see. This part in red is a straight line. It's convexity. This part in blue is quadratic. So actually this looks like what? The second order Taylor series of f. Also related to convexity of f and smoothness of f. So therefore, this number is a very important number. If we chose this number correctly, we actually get strong convexity or smoothness. And this also is something related to something called proximal term. Proximal terms mean distance between you and the previous term. Okay, so there are a lot of things. So now let me expand this to this expression, no change. And then this thing is just quadratic, right? I can write I here, right? And I put the 2 outside, but alpha here. Then this thing, now I call it h. Actually not call it h. This is a second order Taylor approximation. So this term and this term, what's the difference? The difference is I have an identity matrix here and I have an h here. And now detail, I have what? Inner product. So ignore the bracket. It is in the form of this whole vector. I call it u. Okay, I don't care about the difference. This part is h, right? H is, let's say, positive semi-definite. Then I can v lambda v u u, right? What is this? I is vv. Okay, then norm is what? Invariant to what? Orthogonal transformation. I can call v transpose u as a w. Then this thing is w. Why? Because I can move this to the other part. Then I have v transpose. Then I have w w. This thing I do the same thing. Then I have w w. So this thing become this, which is this. This thing, which is this, become lambda w w. So now you see what's the difference between these two. The difference between these two is now I write the full form. The full form is this thing in the end become something 1 over alpha, 1 over alpha, 1 over alpha, blah blah blah, all of them, and then w1, w2, blah blah blah, so on. This thing is what? Lambda 1, lambda 2, blah blah blah, and then w1, w2, blah blah blah. So what's the difference? The difference is I have a same number for all w. Here I have different lambda for different w. What is the Lipschitz constant for gradient? The Lipschitz constant is the largest eigenvalue, and the step size is what? The step size is 1 over L. So the step size here will be 1 over L. That means L. No, lambda. So in other words, if I choose lambda, that means the largest eigenvalue of h or the Lipschitz constant gradient. Actually, I'm having lambda 1, lambda 1, lambda 1, lambda 1. So lambda 1, 1, 1, 1, 1. This one is lambda 1, 2, 3, 4, 5. So here, all is the same lambda 1. Here, different lambda. So that's the difference. And because lambda 1 is the largest eigenvalue, this one is larger than this one. So this is why you have this quadratic expression. Okay. So this is the idea. Okay. This is what I'm just saying. This thing is positive more semi-definite than h because this is the largest eigenvalue. So therefore, this thing is bigger. Therefore, this thing is bigger. So we have the quadratic function. Okay. Now this is the derivation why this thing is a quadratic. So I have this. I want to show arc mean on this is gradient descent. So what I'm going to do? Just do gradient descent. No, deviate. Differentiate this guy. Okay. And then d this thing. I have to d this thing. So this part. And I have to d this thing. This part. Okay. This is constant. Gone. Does not exist. This thing. Okay. This is what? Differentiation of inner product cx. We talked about it in week 1. Give us c. So therefore, this thing. Okay. So this is what I mean. You may say, oh no, there's a shift. I just change rule. Okay. Some rule. We don't care. Okay. Then what? This thing is what? This thing is x something like this. Okay. And then d this, right? This is 2x. The 2 and this cancel out. So the 2 is gone. But we have the 1 over alpha. So we stay there. You may say, oh, there's a x minus xk. No, it's just some rule. In other words, let me say this. I have x minus xk. This I know I write is c. So how do I do this? Well, I do this. Okay. I call this u. Okay. Then what? This is u. No. This is c. Right? And then I done. Then you may wonder, what about the u? Yeah, I can do this, but these are not important. So this is how I do. Okay. What's next? Then now I have this expression. So what I'm showing is what? I'm just showing this thing. Take differentiation. Give me this thing. Okay. Then what? This is the minimizer of this big F if this is 0. So I just solve this thing equals 0. I solve this thing equals 0, right? So first I move this to the other. I multiply everything by alpha. So I have alpha gradient F plus x minus xk equals 0. Then I move this to the other side. Then I move this to the other side. Yeah. So this is gradient descent. So gradient descent is what? Coming from this big F. What is it, the big F? Quadratic function. What's so special of this quadratic function? This alpha is chosen as the Lipschitz constant of the gradient or the largest eigenvalue of h. Then you have this picture. And this is the explanation. So that's why what is gradient descent doing? It's just optimizing a local quadratic over estimator of okay. This is local at this end. Why is local? Because this is very bad approximation of here. It's good here, not here, not here. Because if you keep going on, it's up to the sky. The gap here will be crazy big. Okay. And then what's next? So this is the idea. So therefore, gradient descent. What's gradient descent? Gradient descent descent is xk plus 1 is xk minus alpha gradient, right? This is the easy form. You can write in this way, arc mean of this thing is the same, because you take derivative of this, then you give me this. In other words, what does it mean? This is the basic form of optimization algorithm. If you change this norm to one norm, you have a new algorithm. If you change this to Bregman divergence, you have mirror descent. And then if you add something here, you have other algorithm. Yes, this is the starting point of algorithm, and that's it. So this thing, okay, this thing is what? In a very ugly form. This is something like what? This is something like, let me call it x. I no longer write the transpose, I just write number. Okay, this is constant c, so c, and then plus what? Something alpha x squared. This is what? Something, this is c, this is another c, right? Constant, another c x. So this is something like what? This is something like ax squared plus something cx plus nothing. What I want to do, make it completing a square, make it what? Quadratic form. So I do the completing a square, I will get something like this. So this is what? This is now x minus another c, everything like this. So this looks good. And this actually is the circle I'm talking about. Why? Because what is this expression? Equation of circle, center c. This is now the center. This distance is 2 norm, is circle. Radius is what? Radius is how big you want it to be, scaled up by this number. So this is the circle argument I talked about previously. And then this is the gradient descent. So now gradient descent looks like this. It's very complicated. What is this for? Min f. What happens if I have this? Then I just add it here. There. And then what? If I have this, I want to minimize it, then I just take derivative. Because the idea is derivative of this thing give me gradient descent, right? So now if I have the red part, I do the same thing, I should get an algorithm. That's the idea. But if g is not differentiable, then you have to do this. This is subderivative. You get something else, and this is the starting point of proximal gradient descent. Yes, really that simple. So therefore, this is the summary. Gradient descent come from minimizing a big F. This big F is a quadratic with a well-chosen alpha to make this thing upper bound of your original F. This thing completing the square is this. And now this is for min F. If I have plus g, then I put it here. This is then what? Proximal gradient descent. Done.